Have you ever wondered what time truly is? A question that has puzzled philosophers and scientists alike for centuries. Time, as we perceive it, is a fundamental structure of the universe, not merely a man-made measurement created for convenience. It's an intricate part of the fabric that weaves our reality together. Time is more than the ticking of a clock or the turning of a calendar page. It's a dimension, much like the three spatial dimensions we navigate daily. It's a stream flowing at a steady pace, carrying us from the cradle of the past to the uncertainty of the future. Albert Einstein, the man who needs no introduction, revolutionized our understanding of time with his groundbreaking theory of relativity. He proposed that time and space are not separate entities, but are interwoven into a single continuum known as space-time. And here's the kicker. Time is not absolute but relative, meaning it can speed up or slow down, depending on the speed of a moving object or the strength of a gravitational field. Now, let's delve into another fascinating aspect of time, its unidirectional flow. We all experience time as moving forward, from past to future. We remember yesterday but not tomorrow. We grow older, not younger. This is known as the arrow of time. But here's the paradox. The fundamental laws of physics work just as well backward as they do forward. They're time symmetric. So, why does time have a preferred direction? This question remains one of the biggest unsolved mysteries in physics. In the grand scheme of the cosmos, time is a player that refuses to reveal its true nature. It's a stubborn illusion that shapes our perception of reality. As we delve deeper into the enigma of time, we find more questions than answers. It's a journey that takes us to the very heart of existence, challenging our understanding and pushing the boundaries of human knowledge. Einstein once said, "Time is but a stubborn illusion." So what does this illusion look like? Let's continue to unravel the mystery in our next segment. In our everyday lives, we separate space and time, but what if they're actually intertwined? Let's take a step back and consider a concept that might seem a little bit out of this world. It's called space-time, and it's the idea that unifies space and time into a single four-dimensional continuum. So instead of thinking about space and time as separate entities, imagine them as two sides of the same coin. Now, this coin isn't flat like the ones in your pocket. Instead, it's curved, and the degree of curvature depends on the presence of mass. Massive objects, such as planets and stars, cause space-time to curve around them. This curvature is what we perceive as gravity. So when you drop an apple and it falls to the ground, it's actually following the natural curve of space-time created by Earth's mass. But here's where things get really interesting. This curvature of space-time doesn't just affect how objects move, it also affects how time behaves. This is the concept of gravitational time dilation. Gravitational time dilation is the idea that time runs slower in stronger gravitational fields. So, if you were to stand on the surface of a massive star, your watch would tick slower than if you were floating in the emptiness of space. This isn't just a theoretical idea. It's been confirmed by experiments and is a key part of our understanding of the universe. So, when you're standing on Earth, you're not just existing in space, you're also existing in time. And the gravity of Earth is not just pulling you down, it's also slowing down your clock ever so slightly. This concept of space-time and gravitational time dilation challenges our everyday understanding of space and time. It tells us that space and time are not separate entities, but rather intertwined aspects of our reality. So, if time and space are one entity, does that mean we're constantly time traveling? Why do we remember the past and not the future? Why does time only move forward? These are questions that have puzzled philosophers and physicists alike. To understand this, we delve into a concept known as the arrow of time. The arrow of time is a fascinating idea that time has a direction. It flows from the past, through the present, and into the future. But what gives time this directionality? Why can't we revisit the past or leap into the future? The answer to this lies in the realm of thermodynamics, specifically the second law. The second law of thermodynamics, in its simplest form, states that the total entropy of an isolated system can never decrease over time. Entropy in this case can be thought of as a measure of disorder or randomness. For example, if you break a glass, it shatters into pieces, increasing the disorder in the system. You don't expect the pieces to spontaneously come together to form a perfect glass again. This is entropy at work. Entropy is essentially the reason why time has a one-way direction. It's why we can remember yesterday but not tomorrow, why we grow old but never young. This concept is often referred to as time's arrow. The arrow of time doesn't point backwards because entropy always increases, pushing us forward into the future. But this raises another fascinating question. If entropy gives time its direction, could understanding it help us manipulate time? Could we, in theory, decrease entropy to reverse the flow of time? Well, the answer isn't straightforward. While it's theoretically possible to decrease entropy in a localized system, doing so would increase entropy elsewhere, maintaining the overall increase. This is the cosmic tug-of-war that keeps the arrow of time firmly pointing forward. In essence, the arrow of time is a testament to the relentless march of entropy. It's a reminder that every moment is fleeting, slipping from the present into the past as we move towards an ever uncertain future. If entropy gives time its direction, could understanding it help us manipulate time? As we continue to explore the mysteries of time, perhaps one day we'll find out. Do all creatures perceive time the same way we do? Dive into the world of time perception and you'll find an array of fascinating disparities. It's a realm where the ticking of the clock is not universally uniform, but rather it's subject to a creature's biology and surroundings. Take, for instance, the humble housefly. Ever wondered why it's so darn hard to swat one? Recent studies suggest that smaller animals, like flies, perceive time at a slower pace than we do. To them, our movements are in slow motion, giving them ample time to zip away. On the other hand, larger creatures like elephants might perceive time as passing more rapidly. Their slower metabolic rates and longer lifespans could mean that a minute for us might feel like a fleeting moment for them. But it's not just about size. The way we humans perceive time is a complex interplay of various factors. One of them is age. Ever noticed how time seemed to drag on endlessly when you were a child? But as you grow older, years seem to fly by. This is due to the proportional theory, which suggests that as we age, each moment becomes a smaller fraction of our total life, making it seem shorter in comparison. Emotion too plays a crucial role. Time seems to slow down during moments of intense fear or anxiety, a survival mechanism that allows us to react quickly in dangerous situations. Conversely, time flies when we're engrossed in an activity or when we're having fun. Our attention also shapes our perception of time. When we're focused on a task, time seems to slip away unnoticed, but when we're bored or waiting, each second can feel like an eternity. In the grand scheme of things, these variations in time perception remind us of the subjective nature of time. It's not just a stubborn illusion, as Einstein once said, but also a deeply personal experience that is shaped by our biology, our emotions, and our focus. So time is not only a stubborn illusion, but a subjective one at that. With our current understanding of time, what does the future hold? As we stand on the precipice of scientific discovery, it's worth pondering the potential advancements in our understanding of time. The future of time may not be as linear as we once thought. As we delve deeper into the realm of quantum mechanics, we may find ourselves reconciling with the theory of relativity, giving birth to a quantum theory of gravity. Imagine a world where these two colossal theories, currently at odds, coalesce into one unified theory. Quantum mechanics, with its quirky particles that seem to be in multiple places at once, and general relativity, which paints a picture of a universe woven with the fabric of space-time, coming together to revolutionize our understanding of time. The implications of such a breakthrough are far-reaching and mind-boggling. Our perception of time as a one-way street may be turned on its head. The past, present and future could become intertwined in ways we can't yet comprehend. And then there's the tantalizing concept of time travel. It's a staple of science fiction, but could it become a reality? According to our current understanding of physics, it's not entirely impossible. Einstein's theory of relativity allows for the existence of wormholes, shortcuts through space-time that could, theoretically, be used for time travel. However, the feasibility of time travel remains to be seen. It would require a mastery of unfathomably advanced technology and a deep understanding of the universe's most profound laws. And even if it were possible, it would raise a host of moral and ethical questions. Would we have the right to change the past? And what would be the consequences of doing so? The future of time is a fascinating and largely unexplored frontier. It's a realm filled with possibilities, challenges, and questions that will keep scientists and philosophers busy for generations. As we continue to unravel the stubborn illusion of time, who knows what future discoveries await us?